Hi there. In this lecture we discuss control flow integrity, also known as CFI, which is a very important defense, which again in my original classification falls in the second type, the one where we assume that the attacker can manipulate the data in the program and can read the data in the program, but which prevents them from being able to execute arbitrary code. We discussed both CFI itself and a number of related techniques, including attacks against CFI. Now, we discussed a number of techniques which are all published papers, of course. CFI itself, published in 2005. Out of Control, which is an attack developed by the VUSEC group here, published in Usenix Security 2016. Then another defense, context-sensitive CFI, which we also published. And finally, data-oriented programming, which is another attack. Now, the whole idea of CFI is that we don't want an attacker to be able to run Turing-complete programs, which a ROB chain would allow to do. Instead, we want to restrict the things that attackers can do as much as possible. So we need a solution to restrict the possibilities for an attacker that can override arbitrary code pointers. Now, in the search for better solutions, CFI is one of the main ones. As we've already seen, approaches based on ASLR can help raise the bar for attacker, but they're not completely effective. So we need something better, which even in the face of information leakages, simply does not allow the attacker to do what they want to do. As such, CFI can be considered to be the fallback in case that other approaches failed. So the first line of defense would be the vulnerability mitigations, but as I mentioned before, they're often not practical enough to be deployed or to be fully deployed. So once we assume that the programmer can change anything they like, we have to look for something to prevent them from using that for privilege escalation. Now, the idea of control flow integrity is actually very simple. We only allow legitimate branches and calls. Now, what is a legitimate branch or a legitimate call? It means it is a control flow transfer which the programmer would have expected, and not one that should not be possible within the normal program execution. So it means we want every control flow transfer to follow the control flow graph, which derives from the code itself. Well, here we can see an example. So we have two sort functions, one of which sorts an array from small to large and the other from large to small. Both of them call the same sort function, but they supply a callback function that allows you to order the elements. Now the sorting function calls the callback to determine which one comes first. Right? So either less than or greater than, which then determines whether the list is sorted from small to large or from large to small. Now, in CFI, what we would want to check is we would like to make sure that sort can only call those functions that might be legitimately supplied. So an attacker that can do an arbitrary write might in this case want to override the function pointer supplied to sort and replace it with some code of their own that is part of the ROB chain. What do we want to do? Well, we want to make sure that now the function pointer can only be one of the correct function pointers. So less than or greater than, and that those functions can only return back to the sort function. So even if we override the return address, we cannot return to some other location, as a ROB chain would typically do. So the approach here is that we give every valid target a so-called label or ID. And now every time we perform a branch that is not defined in advance, so an indirect branch where we read the target from memory, every time we verify that we end up at a label that's expected, rather than some weird other label that might be part of a ROB chain. Here we see the control flow graph or CFG of the program that I just showed you. Each of the boxes is one of the functions, and each of the arrows represent a legitimate control flow transfer. So the dashed lines are actually fixed. They are direct calls, and the instruction itself encodes the target of the call. So both of these calls encode the target sort, which is now a fixed address and it cannot be changed by the attacker. All the other arrows are indirect branches. They load their target from memory. And if the attacker manages to override memory, then the target will be different. It will be the target chosen by the attacker. Now, these are all the legitimate control flow targets, and this overview, this CFG, is used to generate the valid targets in the CFI solution. Now, this is what happens if we do CFI. We add a number of labels that specify the different targets for branches. So, for example, ID 11 would be the return location for the call in sort_1. Now, this is a legitimate target for the return instruction for sort, because we know this is the location where sort returns to. Now, likewise, our static analysis shows that the function pointer here could be either less than or greater than. Now, if this is the case, then before we do the call, we need to check whether the target ID is either 41 or 51, and these are the starting locations of the two functions. So we need to verify that we're actually calling one of the functions we're intended to call, rather than some random address supplied by the attacker. Now, when these functions return, they also make sure to check whether the return label is actually correct. So both of these functions can only legitimately return to this location. However, the sort function can return to two different locations because it's called in two different locations. Now, this is known as so-called fine-grained CFI. And this is ideal CFI also in the sense that we have a perfect control flow graph that perfectly matches the possibilities within the real program, and moreover we perfectly enforce it. We never allow any control flow transfer that could not happen in the real program. If we are willing to rely on information hiding, then we can do even better with the shadow stack. Now, a shadow stack is also a form of CFI, but instead of looking at the static control flow graph, it's actually dynamic. It enforces that the return address is the actual return address as it was originally specified. So if we do this, we have to store the location where we need to return to on a separate stack, one that is isolated using information hiding and can therefore not be overwritten by an attacker. So in this case, we perform the call to sort and we store the A. When we perform the call to the function pointer, we store the B. We store them on a separate stack that the attacker cannot target, and then when we return, we read the values from this stack, and we can verify that the value on our regular stack is not corrupted. So we check, is the return address actually B? Is the return address actually A? And now what we achieve is that we can only return to the actual dynamic target. So in this case, we called the function sort from sort_2. And we cannot return to sort_1, which even perfect fine-grained CFI would allow. So the shadow stack only works for the return instructions, because those are predictable, but it provides perfect protection for them, in the sense that we can never return to anything that wasn't the original caller, assuming, of course, the information hiding is effective. So far, we assumed that we know perfectly what the control flow graph actually is, and moreover, we assume that we perfectly enforce this control flow graph. Now, this is not always possible, and it's not always practical. So, to know the precise control flow graph, we need static analysis. Now, static analysis cannot give us all the possible information. We may not be able to determine whether a particular function pointer can actually appear somewhere. Moreover, we need source code or debug information to be able to derive the control flow graph, because if we have only binary code, we're missing even more information that would be needed to derive it. Moreover, this ideal CFI has a large performance overhead because we need to check for multiple labels every time we perform a call, an indirect call, or a return instruction. So this, even though it has some reasonable protection, is not always practical. What we can do instead is doing a coarse-grained CFI. Now what this does is, rather than having an arbitrary number of labels depending on the control flow graph, it has only a few labels that are fixed. For example, all the call sites could have the same label, and all the function entry points could also have the same label. Now this means that we can no longer call an arbitrary address. We can only call functions that are actually targets for indirect calls, nor can we return to an arbitrary address. We can only return right after a call instruction, but we don't necessarily need to jump to the right function, nor return to the correct return address. Now, the nice thing here is that now we not only reduce the overhead, but this also applies to binary-only software that provides less information about the control flow graph. Now, if we apply coarse-grained CFI to the example that I showed before, this is what we get. The control flow graph is still the same, of course, but now more returns are possible. We have just two IDs. So ID 1 is the start of a function that can be targeted by an indirect call, and ID 2 is the location where a return instruction can return to. So now, for example, this return instruction at the end of greater than can return to its correct location, which is here right after the call to this function, but it might equally return to other locations where other calls were made. Now in the real CFG, it's not ever possible to return to these locations, but of course an attacker could force this. And now that we loosen CFI, CFI will also allow it. Now this comes with the benefit of providing better performance. So if normal CFI is too slow to deploy but this works, this can still be a good choice for security. It turns out, if we deploy this system and we measure the number of gadgets that we can still use, so the number of locations we can jump to, it eliminates 98% of these gadgets. So the number of gadgets we can use to construct a ROP chain become dramatically less. Of course, the question is that actually enough? Now, then we need to look at the different approaches that exist. So there are several approaches that use coarse-grained CFI with a different number of labels. So for example, Abadi CFI simply has a single label for all possible indirect control transfers. Bin CFI, which as the name implies, is readily applied even in case of just binaries, has one class for return and indirect jump instructions and another for indirect call instructions. Now, CCFIR is another one, and it has separate categories for return instructions, but also return instructions in sensitive functions, and then of course indirect calls. So the sensitive function in this case is a function that allows an attacker to do special things. For example, a call to mprotect, which allows you to map some memory as writable or executable. So if you make this distinction, you can at least make sure that these sensitive functions are not easier to access. Still, the question is this actually enough to stop a ROP attack? So we know that the number of gadgets is dramatically reduced, but perhaps it was already far more than the attacker needed. So it's not clear that this actually helps enough. The question is then not so much how many gadgets are left, but what are the gadgets that are left, and is there some way that we can use these gadgets to still perform the ROP attack? Now this is the topic of the paper Losing Control, published by the VUSEC group here. Now the old ROP targets are out. Right, so normally we would like to just be able to jump to any simple return instruction. We could even use unaligned instructions, that is, jump to the middle of an instruction and the CPU will interpret it differently. And also a call to a non-function no longer works. So even coarse-grained CFI eliminates all these possibilities. The question then becomes, can we still perform a ROP attack? So which are the gadgets that are still left? So there are some specific types of gadgets left. So one is the entry point gadget. We can, if we want to construct a ROP chain, we can call an entry point gadget using an indirect jump and then go up to the next indirect jump or the next return instruction. At that point, we can take over control again by supplying the correct address there where we want to go to. So this is the entry point gadget, and after the first indirect call or jump, we also have a call site gadget. So the call site can be targeted by a return instruction which can return to the next instruction after a call site. So these two types of gadgets are now still available if we use coarse-grained CFI. Let's say we want to use these gadgets to call a function, then we have several possibilities. So the first here is a call site gadget that is used to perform an indirect jump. So here we start right after the call instruction. Because we're using a call site gadget, we need to go there from a return instruction and then we end up at an indirect call. Presumably, because we control the memory using our arbitrary write vulnerability, we can set the pointer to call any entry point function. Right? So we can only call the entry point gadgets there, but we can choose whichever one we want using the arbitrary write, and then we end up at the return again to jump back to some call site gadget. The second one is similar. It also uses a call site gadget, but it calls a fixed function. So if we have a gadget like this, we can call fixed underscore func, even if it's not a target for indirect calls. So we may need this, for example, to call sensitive functions. And finally, we can also have a gadget that starts in an entry point. So this starts at the start of a function and then ends up in an indirect call. So we have all these possibilities to be able to call different functions in the program and use their ability to complete our ROP chain. The critical step to be able to do ROP is to be able to link gadgets. So each individual gadget can do only a small task for us, but if we can combine an arbitrary number of gadgets, we can use them to essentially compile a program. Now we can easily link gadgets of the same types. So if we have call site gadgets, then we end up at a return instruction, and the return instruction can go to another call site gadget. If this call site gadget eventually ends up at a return instruction, then we can jump onto the next and complete the chain. Now, likewise, if we have entry point gadgets, we can go up to a call and then call a function whichever we like, which is another entry point, and so we go through a chain of gadgets again. Now the other question is, what if we want to combine the different types of gadgets for better expressiveness of our code? Now let's say we want to move from one type of gadget to the other type. So let's start with the call site gadget. In this case, we have a return instruction which returns to a call site. So this is the location right after an indirect call. At that point, we can continue onward to the return instruction and now return to another gadget, another call site gadget, because that is the only place that a return instruction can return to. However, we now pick one that ends in an indirect jump, right? In this case, an indirect call, and the indirect call calls another function. This function we can specify, and we specify a function that performs an indirect call again here. Now, at this point, we can continue onward with further entry point gadgets. So we managed to link the one type to the other. Well, what about the other way around? Let's take a look. So we start off with an indirect call, which allows us to go to an entry point gadget. Now, we call this function, which does another indirect call, and it goes to function B, which also performs an indirect call. Now what is the trick here? The trick is that we can corrupt the stack. And if we corrupt the stack, we can change the return address again. Now we corrupt the stack by calling a function with an incorrect number of parameters. Now in this case, if parameters are pushed onto the stack, it means that we're misaligning the stack. And when we return, it's no longer consistent with how it was before. Now, this we can use to make sure that we don't return to the correct location. Right, so this call here pushed the right return address onto the stack. But now, if we corrupt the stack by misaligning the number of parameters, then we no longer end up at the correct return address. So the attacker is now presumed to control the return address, and we will return here to a call side gadget. So it turns out we can link all the gadgets even if they are different types. To show that this attack actually works, we used Internet Explorer 8, of course, which was a recent browser at the time of the publication, applied ASLR as well as data execution prevention, and also used CCFIR to protect Internet Explorer 8 against ROP attacks. Now, what did we do? We abused a particular heap buffer overflow, and this heap buffer overflow provides the arbitrary write primitive that we need. Now, we spray the heap with desired exploitation data, which means that, for example, in JavaScript, we allocate a lot of arrays that have the data that we want to use. Now, we trigger the vulnerability. We get control of an indirect jump. So this indirect jump allows us to go to any indirect jump target, and from that point onward, we executed the linked gadgets, creating a ROP chain, and this way we show that this actually works. We managed to get a ROP chain executing even in a program protected using coarse-grained CFI. So clearly this is not sufficiently effective to actually prevent an attacker from exploiting Internet Explorer 8, which at the time of the publication was in fact a very desirable target for attacks. Clearly, CFI is not perfect. Even if CFI manages to correctly enforce the control flow graph, there are still variations that an attacker can cause, and this is undesirable. Because even if just a few gadgets are left, as we've shown with the losing control paper, it is often still possible to perform an attack, even with this a limited number of gadgets. Now, what can we do to solve this? Context-sensitive CFI is a promising direction. So the default regular CFI poses the question, can this particular call or jump or return instruction ever target that particular instruction? If the answer is yes, then the control flow transfer is allowed. The shadow stack checks that the return actually matches the latest call, so it must be exactly right. But this only works for the return instructions, which in the field we also refer to as the backward edge. So it's the backward edge in the sense that it returns to a previous location in the control flow graph. Now, can we do a similar thing for the forward edge, where we have indirect calls? It turns out to some extent we can. We can use so-called context-sensitive CFI. Now, in this case, we verify not only that the target is ever possible at all, but we verify that it's possible using the current call graph, which is as close to the shadow stack approach that we can get, but now for indirect call instructions. And VUSec made the first practical implementation of something like this, namely Path Armor. Now let's say that we managed to develop context-sensitive CFI to the point where we can ensure that the CFG is never ever violated. Now there's the question, would an attacker still be able to perform an arbitrary computation? Which is in the end the goal that a ROP attack tends to have. The answer is actually yes. And why is this? Well, even though the control flow graph is maintained, the data also matters. The data that you provide as the input for a program guides the code through the CFG, which means that if we change the data, we also change the control flow, even if it still matches the original control flow as allowed by the program and has to be allowed by CFI. This leads to an approach called data-oriented programming. So this is basically a variation of return-oriented programming where we don't need to violate the CFG. Instead, we only override the data, for example, using a buffer overflow, and then think of a clever way to construct arbitrary computations. Now, to do this, a typical approach would be to use a dispatching loop. So we find a loop somewhere in the program that we can influence using data. Now, this has to be a loop because the loop executes as often as the attacker desires. This allows the attacker to make arbitrary compositions of whatever they want to do with their data. Now, the loop should perform a number of operations, including necessary gadgets for the attacker. So the attacker has to be able to trigger particular operations with the data that together allow a full set of operations. So the attacker controls the values and the pointers used in those operations using the arbitrary read and write primitives that the attacker has. And then, using this dispatching loop, the attacker can essentially supply the right data to perform the arbitrary computation using these gadgets, which take as operands the values and pointers. This simple program shows an example of how you could perform data-oriented programming. Now, this function that we show here uses a socket to read data, and there's a buffer overflow in the read. So now the attacker is able to override all the control variables, and it's important to consider that this happens in a loop. So the attacker can do this as many times as they want, overriding the values each time and using those values to control what happens inside the loop. Inside the loop there are some conditional gadgets. So in this case, by manipulating the value of type, the attacker is able to select which of the if statements actually executes. And then the different if statements provide the gadgets that the attacker might need to perform a full computation. For example, if the type field is set to stream, we have a so-called dereference gadget, where we can supply a pointer and get the value stored at that location. In the other case, we have both an assignment gadget and an addition gadget, which also help us to perform computations. So now, based on the data that we supply, we can make the program again do whatever we want, essentially, even though we do not violate the control flow graph. Returning back to the general case, the approach for data-oriented programming is as follows. First, we find the gadget dispatcher, so we essentially need to go through the loops in the program and see which of the loops could be controlled by the attacker to make sure we can execute it an arbitrary number of times. Then we need to look for gadgets within these loops, identify them and classify them so that we can use them for the payload. Now, we have a workload, which could be specified as a program, for example, that we need to convert into a sequence of gadget operations. So after we know which gadgets we have available, we need to figure out how to perform this workload using the available gadgets. Next, we build the buffers that can trigger the operations. So this is tweaked especially to the loop that we're using as a dispatcher. It must force the loop to perform the operations that we want. And finally, we send those to the target machine. And then the data will guide the code to perform the computation that we want, even though this computation was not originally intended, because now we can change the data that control how the program is executed from the attacker. So in this story we showed that even with very good CFI, we can still do Turing complete computation. Now, we should ask ourselves, however, is this in fact of practical relevance? And this is something that's up for debate, actually. So first of all, Turing completeness with data-oriented programming is something you can only do if you have the exact right gadgets. So if you have a simpler program that doesn't have as many gadgets, we might not be able to do it. Moreover, and this is perhaps the more fundamental question, is arbitrary computation actually very useful? So in the academic world, we basically assume if we can do Turing-complete computation, we take over the program completely. Now, to some extent, this is true because it means that we can control the actions of this program itself. However, to do anything else on the system, we need system calls. And we can only do those if the program allows us to do it from the data-controlled loop. So it's questionable whether we can do any system calls, and if we cannot, whether we can achieve meaningful privilege escalation, which was after all the goal. So the conclusion could be, CFI is not perfect. We can do a lot of things even in the theoretical ideal case of CFI, but one could argue that perhaps these things are not as useful as the things we could do without CFI. So as such, CFI still tends to be a valuable addition to security, and it is in fact by now widely used. If you have an approach that's sufficiently efficient, it can really raise the bar for attackers by a lot, and perhaps even eliminate attacks in some cases.